Point 2. Work and power. Energy is a measure of an object's ability to do work. Suppose you lift your book over your head. The book gets potential energy, which comes from your action. Now suppose you lift your book flat, then lift it again slowly, fast, and then lift it again slowly. The energy is the same because the height is the same, but it feels different to transfer the energy fast or slow. The differences between moving energy fast or slow is described by power. Power is the rate at which energy flows or at which work is done. This section is about power and its relation to work and energy. The word work is used in many different ways. You should always check over your work before handing in a test. Your parents go to work. The toaster doesn't work. You work with other students on a group project. In science, work has a different and very specific meaning. Work is a kind of energy you either use or get when a force is applied over a distance. Work is energy and is measured in joules, just like other kinds of energy. You do 1 joule of work if you push with a force of 1 newton for a distance of 1 meter, figure 6-7. You may remember this is exactly the definition given for the joule, the unit of energy. Energy is defined in terms of the amount of work that can be done. If you have a lot of force for a great distance, science makes the everyday meaning of work much more precise. By making work equal to force multiplied by distance, we can calculate exactly how much work is done in any given situation. Doing work always means transferring energy. The energy may be transferred to the object you apply the force to, or it may go somewhere else. You may increase the potential energy of a rubber band by exerting a force that stretches it. The work you do stretching the rubber band is stored as energy in the rubber band. The rubber band can then use the energy to do work on a paper airplane, giving it kinetic energy, figure 6-8. You can do work on a block by sliding it across the level table. In this example, though, the work you do does not increase the energy of the block, because the block will not slide back all by itself. It does not gain the ability to do work itself, therefore it gains no energy. The work you do to slide the block is done to overcome friction. The block does gain a tiny bit of energy because its temperature rises slightly from the friction. However, that energy comes from the force of friction, not from your applied force. Sometimes force is applied to an object, but no work is done. If you push down on a block sitting on a table and it doesn't move, you have not done any work, force A, in the scientific sense. You used your muscles, but your force did not cause the block to move, and therefore no work was done. Work is only done when the force causes motion. There are times when only some of the force does work. Force B is applied at an angle to the direction of motion of a block. Only a portion of the force is in the direction the block moves, so only that portion of the force does work. The most effective force is force C. All of force C acts in the same direction the block moves. Work, you multiply the force by the distance the object moves in the direction of the force. If you lift a block with a weight of 1 newton for a distance of 1 meter, you do 1 joule of work. 1 joule of energy is transferred from your body to the block, changing the block's energy. When thinking about work, you should always be clear about which force is doing the work on which object. Work is done by forces. Work is done on objects. If you lift a block 1 meter with a force of 1 newton, you have done 1 joule of work on the block. An object that has energy is able to do work. Without energy, it is impossible to do work. In fact, one way to think about energy is as stored work. Anything that has energy can use that energy to do work. A falling block has kinetic energy that can be used to do work. If the block hits a ball, it will do work on the ball and change the ball's motion. Some of the block's energy is transferred to the ball during the collision. Michael and Jim each lift a barbell weighing 100 newtons from the ground to a height of 2 meters, figure 6-9. Michael lifts quickly and Jim lifts slowly. Michael and Jim do the same amount of work. However, Michael's power is greater because he gets the work done in less time. Power is the rate at which work is done. The unit for power is the unit of work, or joules, divided by the unit of time in seconds. 1 watt is equal to 1 joule per second. The watt was named after James Watt, the Scottish engineer who invented the steam engine. Another unit of power is the horsepower. He expressed the power of his engines as the number of horses an engine could replace. 1 horsepower is equal to 76 watts. Michael and Jim do the same amount of work since they lift the same weight the same distance. Use the relationship work equals force times distance. The force is the weight of the barbell, 100 newtons. The work is 100 newtons times 2 meters equals 200 joules. Each of them does 200 joules of work. Michael's power is his work, 200 joules, divided by his time, 1 second. Michael has a power of 200 watts. Jim's power is 200 joules divided by 10 seconds. Jim's power is 20 watts. Jim takes 10 times as long to lift the barbell, so his power is 1/10 as much. The maximum power output of the average person is a few hundred watts. Stop here and answer these questions.